One of the very interesting ideas in statistics is this idea called hypothesis testing. It's a beautiful, elegant, and mesmerizing idea. I really loved it when I first saw it. So let me try to explain you this concept using an example. So let's assume I have two classes. I have, let's say, classroom 1 and classroom 2. And let's assume I have taken heights of students. I've taken 50 students. Let's say student 1, student 2, so on and so forth. Let's assume I have measured heights of 50 students from class 1. Okay, so let's say their heights are 160, 152, so on, so forth, so on, so forth, 148. I've also measured, so I've taken my second class. Let's assume my class 2, and let's assume I have measured the heights of, again, 50 students here, 1 to 50, right? So let's assume I get 162, 156, so on, so forth, 182. Let's assume I get a bunch of 50 numbers here, 50 numbers here. The question on my mind is there a difference? Is there a difference in heights of students, in class 1 and class 2? Okay, and I want to be very, very sure about answering this question. I want to be absolutely sure, or I also want to quantify how sure am I when I say that class 1 students typically tend to be taller than class 2 students, or class 2 students tend to be typically taller than class 1 students. To answer this question, you might say, okay, this is very straightforward. Why don't I just plot, right? You could say, okay, or you could say much more simply that, okay, since we know histogram, right? Let's look at that. So let's assume I plot the histogram of heights of students of class 1, which looks like this, let's say. Let's assume the heights of students of class 2 looks like this. Okay, this is your height. And this is your class 1 and this is your class 2. Now we want to understand there is a small difference, right? What do you do now? You say, okay, since the mean of heights of class 2 is slightly greater than mean height of students in class 1, right? Because if you look at it, this height mean is here. This is your mu2. And if you look at this, this is your mu1. So you could say, okay, your mu2 is greater than mu1, hence students in class 2 are taller than class 1. But how confident are you? The gap is so damn small, right? How do we quantify this and be very, very scientific about explaining if there is actually a difference in heights of students, right? To do this, there is a process called hypothesis testing, and I'll first explain the process at a very high level, and then we'll go and solve this problem using a very interesting technique called permutation testing. Okay, so the process has these following steps. The first step is called choosing a test statistic. Choosing a test statistic, what does a test statistic here mean? Come up with one number that you will use to say that students of class 2 are taller than students of class 1. Of course, the obvious test statistic in this case could be the difference in mean height of students in class 2 and mean height of students in class 1, right? Here mu2 is nothing but mean height of class 2 students. Okay, and similarly mu1 is the mean height of class 1 students, right? Now if this value is small, if this value is 0, right, then you're sure that yes, there is no difference in heights of students between class 2 and class 1, right? So this is what I mean by a test statistic in our case. The second step is you define something called a null hypothesis. These terms might sound alien to you, but I'll just quickly explain this. A null hypothesis is often written as H0. So this whole method follows something called proof by contradiction. It follows a very, very interesting idea in proving called proof by contradiction. Let me explain this. Let me explain this step by step. This is a very, very interesting idea, but there's a small leap of understanding that we all have to make. So let's just bear with me. Just bear with my terminology. Let's go step by step, very carefully. If required, we'll spend more time on this concept. Okay, so what is a null hypothesis? A null hypothesis is an assumption that you're making. Suppose my null hypothesis in this case, typically for in problems like this, my null hypothesis is things like, okay, that there is no difference, in heights, there is no difference in mu1 and mu2. So typically your null hypothesis are status quos. Okay, or it's a simple, it's basically saying that there is no difference between the two things. Then there is a concept called alternative hypothesis, which is also written as H1. And what is alternative hypothesis? Alternative hypothesis is nothing but the inverse of your null hypothesis. It is nothing but saying that it's nothing but a hypothesis that there is a difference in heights of students in class 1 and class 2. Okay, so in this process, as I said, it's a method of proving by contradiction. Let's see how that works. So I assume that my null hypothesis is true, and I prove that my null hypothesis is incorrect, and hence I should accept my alternative hypothesis. Okay, or I assume that my null hypothesis is true, and I find that yes, my null hypothesis is true with a very, very high probability, and hence we should accept our null hypothesis. So in this case, in this simple case where we are testing difference between two population means, right? We have two populations, right? This is the population of students in class 1, and this is a population of students in class 2. And what we are measuring here is the mean, or the difference in means of these two populations. In problems like this, typically a null hypothesis is that there is no difference in these means. The third step is we compute something called a p-value. Let me explain what this p-value means. The p-value here, and this is the computational part. This is the interesting math part, or this is the interesting computer science part, right? P-value basically says what is the probability of observing your whatever you have observed. Suppose I have taken 50 students here, and I got my mean to be mu1, and I got my mean to be mu2. So it says what is the probability of observing your values. Your test statistic is mu2 minus mu1, right? What is the probability of observing? This is my test statistic, right? So let me just call this as x here. Okay, so what is the probability of observing a value of x, okay, or a difference of x, if my null hypothesis is true? Let's understand what this means. What this means is, imagine, so let's assume that my null hypothesis is true, which means there is no difference. Okay, which means between my class 1 students and my class 2 students, between my class 1 students and my class 2 students, there is actually no difference. Okay, but because we have only sampled 50 points here and 50 points here, of course, when you sample a bunch of points, your means, the mean that you computed is actually mean of this 50 points, right? So assuming that your null hypothesis is true, which means assuming that your class 1 and class 2 heights are roughly the same, what is the probability of observing a value of x? So for example, let's assume I took 50 points here, and I found my x to be, let's say, 10 centimeters, right? Or the average, or the difference in the mu's to be 10 centimeters. Then the immediate question is, what is the probability of finding a difference of 10 centimeters, assuming that my null hypothesis is true? If let's say the p-value, let's assume if the p-value is, let's say, 0.9, what does it mean? It means that, let's assume if my p-value is 0.9, what does that mean? It means that if my null hypothesis is true, I don't know how to compute p-value yet. We'll see how to compute it. Let's assume somebody gave us the p-value. Okay, let's assume the p-value is 0.9. Let's understand what it means. This is a very, very interesting concept, and something that we have to digest very carefully, right? So if p-value is 0.9, what it means that the probability of observing a difference of 10 centimeters in the means of heights of students of class 1 and class 2 is 0.9 if my null hypothesis is true. And what is null hypothesis? Null hypothesis is that there is no difference in the class, in the heights of the class, in the heights of students of the classes. So even if there is no difference in the heights of the students of the class, I could observe 10 centimeter difference when I take 50-50 samples here. Here, of course, if I just took only one sample here, right, I'll see much more difference. Instead of 50 samples, if I took 5,000 samples, right, then of course, I don't have 5,000 students in each of these classes, but let's assume I took many more samples, let's say 5,000 samples, then this will be much smaller. Probably I'm finding this difference just because I've taken too few samples, right? Now, the other way of it, which is, so if your p-value is high, you say, okay, even if these two classes had the same height, I could observe a 10 centimeter difference easily, and hence I just accept. So if p-value is high like this, I say I accept my h0. I accept my hypothesis 0, which is that there is no difference. Now let's assume if p-value, let's say p-value is 0.05, which means 5%. So what does this imply now? If your p-value is small, it means that there is a probability that there is a 5% chance. What does this mean? It means that there is a 5% chance or 5% probability that the difference between mu1 and mu2 is 10 centimeters, right? If my h0 is true. If my h0 is true, let me read it in English again. What it means is, if my probability, if let's assume, what is h0 being true mean? It means that students of class 1 and class 2 have the same height, right? If that is true, if that was true, then my chance of finding a difference of 10 centimeters between mu1 and mu2 is only 5%. So if p-value is small, you would say that your h0 probably is incorrect. Then you say we reject our null hypothesis, or we accept our alternative hypothesis, right? This is very, very important. This idea of accepting and rejecting, this is slightly confusing. The first time I learned it, I never understood it very clearly, because this is proof by contradiction, right? So it's very, very important. I recommend, if you have not digested this concept, to redo this video, as in to go through this video again to understand why to accept or reject a hypothesis based on the p-value, right? So this is extremely important idea. So just in the interest of time, let me repeat it. Okay, a p-value, we don't know how to compute it. We'll see it in the next video. Let's assume we have a p-value, and a p-value is nothing but the probability of observing a difference of 10 centimeters in our case, assuming that the null hypothesis is true. And what is a null hypothesis being true? Null hypothesis being true basically means that there is no difference in heights of students of these two classes. Now, if the p-value is high, then you would say yes. Let's assume there is no difference between the students of heights of students of this class, of these two classes, and the chance that I observe a 10 centimeter difference when I take 50-50 samples is about 90%. And hence, and my observation today is for the specific samples that I collected is also 10 centimeters. And the probability of this happening is 90%, even if my null hypothesis is true. And hence I accept my hypothesis. But if such a p-value is small, which means there's a very small chance, there's a very small, assuming, so let me read this in English. What this means is, assuming that there is no difference in heights of students in class 1 and class 2, that's what my h0, right? Assuming that there is only a small 5% chance that the difference in means would be 10%. Which means, in this specific case, which means when I have these observations, the chance that your null hypothesis is true is very small, which means we should reject it and accept our alternative hypothesis. And our alternative hypothesis is that mu1 and mu2 are different, right? This is a very, very important idea. If you have still not understood it, I strongly recommend you to review this video and try to digest it. We'll show how to compute p-values in the next video.